Before I move on, I want to make some remark on binding constraints. Let me remind you what does it mean by inequality constraint to be binding at a point P. It means nothing else than when you put the point P into your constraint function, the equality holds. Or in other words, h at P equals to B. Okay? So the P will satisfy the equality of your inequality constraint. So let's have a look on this example. I want to do an example with you. That is, we try to maximize the objective function. In this case, the objective function is given by this, x times y times z plus z, subject to 4 inequality constraints. The first one is x squared plus y squared plus z squared less than or equal to 6. The next 3 is, it's very symmetric and very simple. X greater than or equal to 0, y greater than or equal to 0, and z greater than or equal to 0. So this the last three, x greater than or equal to 0, y greater than or equal to 0, and z greater than or equal to 0 are usually called non-negativity constraint. Okay, and then they are very commonly used in optimization problem. Because, for example, if you try to, in reality, you try to optimize your production, then all the inputs you put in, for example, x, y, z, they are input, right? And all the inputs are obviously greater than or equal to 0 because you never have negative input. So this kind of non-negative constraints are very common in realistic optimization problem. But the first thing we need to do here before we do anything else is we realize that, okay, the first inequality, okay, is less than or equal to, but these 3 are not. So the first thing we have to do is to rewrite the last 3 as x less than of negative x less than or equal to 0, negative y less than or equal to 0, and negative z should be less than or equal to 0. Because we need to make sure that the inequality sign is pointing in the correct direction. Part A. Write down the complete set of first order conditions for this problem. So the first thing we need to do is to write down the Lagrangian. So Lagrangian. What is the Lagrangian in this case? The Lagrangian L equals to the objective function. So in this case, x times y times z plus z. So this is our f. And then minus lambda 1, okay, the first inequality constraint comes from x squared plus y squared plus z squared less than or equal to 6. Therefore, we put down x squared plus y squared plus z squared minus 6. And then minus lambda 2, the next inequality constraint is minus x less than or equal to 0. So we just put minus x. And that's all. Lambda 3 minus y, lambda 4 minus z. Okay? And then first order condition. So remember, we have 4 kinds of first order condition. The first kind is equality. And they're given by the derivative of L with respect to x, y, z respectively. So Lx equals to yz minus lambda 1 to x. And then, this minus lambda 2 times lambda minus 1, so plus lambda 2 equals 0. And then the next one, differential with respect to y, you get xz minus lambda 1 to y. And then when you differentiate with respect to y, okay, the only guy survive is this. When you differentiate this with respect to y, you get minus 1, so you get plus lambda 3. And the last one, differentiate with respect to z, be careful, you have an extra z here. So it's xy plus 1 and minus lambda 1 to z and plus lambda 4 equals 0. So these are the equality constraint. And then you have the complementary slackness. Complementary slackness that come from each inequality constraint. So you want this to equal 0 respectively. Okay, so the first one will be lambda 1 times x squared plus y squared plus z squared minus 6 equals 0. The other one is lambda 2 times minus x equals 0, which is the same as lambda 2 times x equals 0. Okay? And then you lambda 3 times y equals 0, lambda 4 times z equals 0. So in this case, we get 8 equalities. 8 equalities in total. 1, 2, 3, 4, 5, 6, 7. Sorry, 7. Counting incorrectly. Sorry. 7 equalities in total. But these are not all. You have 2 more kinds of constraint. Inequality. Equality basically are the given set of inequality constraints. So they are here. So they are x squared plus y squared plus z squared less than or equal to 6, and the x greater than or equal to 0, y greater than or equal to 0, and z greater than or equal to 0. And then the last one is the positiveness of multipliers. Positiveness of the Lagrange multiplier. So in this case, you have all the lambda 1 greater than or equal to 0, lambda 2 greater than or equal to 0, lambda 3 greater than or equal to 0, and lambda 4 greater than or equal to 0. Okay? So these are all the first order condition. And then in this case, you get 1, 2, 3, 4, 5, 6, 7, 8, 8 inequality constraint. Okay? So 8 inequality first order condition. Okay, part B. Part B is interesting. Explain why this constraint is always binding at any solution to the first order condition. So, explain why. So we want to show x squared plus y squared plus z squared is always equal to 6. Okay? We need to explain why the constraint is always binding. That means that why the equality is always whole. Okay? Why the equality is always whole. So what's the proof? Well, if we're not too sure why the equality is always true, let's suppose by contradiction that x squared plus y squared plus z squared is strictly less than 6. Okay? Strictly less than 6. Then, what will happen? Look at this equation here. If x squared plus y squared plus z squared is strictly less than 6, then this is not 0. This is not 0. So this enforces lambda 1 has to be 0. So let me label the equation. So you have 1, 2, 3, 4, 5, 6, 7. Then if this is strictly less than 6, then by equation 4, we know that lambda 1 has to be 0. Okay? And then, if lambda 1 has to be 0, what's the problem? Well, where do I have lambda 1? Well, I have lambda 1 here, here, and here. If you think about that, it turns out the problem happened in the third equation. Why? Okay, I will write down why. So, then the third equation becomes xy plus 1, and then lambda 1 is 0, so this guy dies, so plus lambda 4 equals 0. Okay? So, that means that xy plus lambda 4 is minus 1. Is that possible? Think about that. Well, look at my inequality constraint. The inequality constraint tell me that x, y, and lambda 4 are all positive. So the left-hand side should be positive. So in particular, it's impossible for the left-hand side to be equals to minus 1. So which is impossible? Impossible because as x, y, and lambda 4, they're all greater than or equal to 0. So this is a contradiction. So it's impossible that x squared plus y squared plus z squared is strictly less than 6. And then because I know that x squared plus y squared plus z squared is less than or equal to 6, so well, inequality cannot hold, so equality must hold. So hence, x squared plus y squared plus z squared equals 6, okay? Or in other words, the constraint x squared plus y squared plus z squared less than or equal to 6 is always binding. And that's it. The point I want to make about this example is that although for an inequality constraint problem, the first order condition looks like a nightmare, but actually the inequality here will give you some restriction on what kind of solution you can have here. Okay? So it turns out this system of equation is not as complicated as you think, given this set of inequalities. And this is a very basic example how we can use the inequality to simplify the equations here. Okay? But I will do more examples. In particular, at the end of this week, we'll do a complete example together. And then we'll see how this kind of trick would work in a more general sense. Okay?